Right now, you are sitting inside a hole in the universe, a hole so wide that light needs 2 billion years to cross it. Around us, galaxies thin out, stars grow scarce, and for decades, almost nobody realized we were living inside it. This giant empty region may be lying to us. It could be twisting what we see, making the whole universe look like it is growing faster than it truly is. In the moments ahead, we will fall toward its hidden walls, listen to the faint echo of the Big Bang for answers, and watch our best theory of the cosmos begin to crack. If the biggest mysteries out there pull at you, tap like and subscribe so you stay with us the whole way. So take a breath, look up. We are about to leave the map behind. Step outside tonight, far from city lights, and look straight up. The sky looks crowded. Thousands of stars, a smear of the Milky Way, maybe a planet glowing steady near the horizon. It feels like we live in a busy corner of the cosmos. That feeling is wrong. Every star you can see with your eyes belongs to our own galaxy. All of them. Even the farthest specks sit inside the same spinning city of stars we call home. To really see where we live, you have to pull back, way back, past the Milky Way, past our neighbor galaxies, past the clusters and the superclusters, until whole galaxies shrink to single points of light. Do that, and a shape appears. The universe looks like a sponge, or the foam on top of a soda. Bright threads of galaxies stretch across the dark, meeting at glowing knots where thousands of galaxies pile together. And between those threads sit enormous empty rooms of almost pure nothing. Scientists call this the cosmic web. The bright parts are the walls, the dark parts are the voids. And here is the first strange clue. When astronomers mapped our own address inside that web, our patch came back oddly quiet. Fewer galaxies than expected, more darkness than there should be. At first, that seemed like a small thing, maybe a gap in the data, maybe our telescopes had missed a few faint smudges, but the quiet did not go away. The more carefully they counted, the emptier our neighborhood looked, and the emptiness kept growing. Picture the universe as a giant city seen from an airplane at night. Bright neighborhoods glow in clusters, connected by lit-up highways. Now imagine your own house sits in the middle of a huge dark park, miles across, where the streetlights simply stop. You would want to know why. You would want to know how big that dark stretch really was. That is the question a small team of astronomers started asking. They were doing something that sounds almost boring. They were counting galaxies, one by one, across a wide slice of sky, to measure how crowded our part of the universe truly is. They expected an ordinary answer, an average patch, roughly as full as any other. Instead, the numbers kept coming back low, too low, as if someone had scooped out a giant spoonful of the universe and left us floating in the hollow. For a long time, most cosmologists assumed we lived in a fairly typical spot. Nothing special, a regular galaxy in a regular region, following the same rules as everywhere else. That assumption sits at the very heart of how we study the cosmos. Shake it, and a lot of other ideas start to wobble. So the stakes were bigger than they look. If our corner really was unusual, then everything we measure from here, including how fast the whole universe is growing, might carry a hidden bias built right into our address. The team pushed on. They aimed their instruments at a special kind of light, one that could see through the clutter and reveal galaxies others had missed. What they found in that light would turn a quiet counting project into one of the strangest puzzles in modern science. To understand what the team found, you first need to understand emptiness. Real cosmic emptiness. Because a void in space is stranger than any empty room you have ever stood in. Start with the cosmic web again. For a long time, people pictured the universe as evenly sprinkled with galaxies, like grains of salt spread on a black table. Then the big galaxy surveys arrived, mapping millions of galaxies and their distances. The salt had clumped, gravity did the clumping. In the young universe, some regions started with a tiny bit more matter than others, a whisper of extra density. Over billions of years, gravity pulled matter from thin places toward thick places. The rich got richer, the empty got emptier. Matter drained out of the low spots and piled into walls and knots. The result is the foam we see today. Galaxies gather along thin sheets and stringy filaments, like water beads clinging to a spider web after rain. Where filaments cross, giant clusters blaze. And trapped inside the web sit the voids, the vast bubbles of near nothing that make up most of the universe by volume. Here is the part that surprises people. Voids are the main feature of the universe. If you measured space by sheer room, most of it is void. The glowing walls and clusters, all the galaxies and stars and planets, live in the thin borders around enormous empty bubbles. We tend to notice the light. The universe is mostly the dark between. A typical void is already gigantic by any human measure. Light, the fastest thing there is, might take 100 million years just to cross one. Inside, a lonely galaxy could drift for that entire span with almost no company, its nearest bright neighbor impossibly far away. If Earth sat in the deep center of an average void, our night sky would look nearly black even through a strong telescope. Now hold that picture because it makes the discovery hit harder. The team was asking whether our whole region, the space around the Milky Way for a staggering distance, might itself be a void. A hollow so wide it would dwarf ordinary voids and swallow thousands of galaxies worth of missing matter. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies. As the dough rises, every raisin drifts away from every other. That is cosmic expansion. But now imagine one region of the loaf where the raisins are spread far thinner than the rest. A hollow pocket in the bread. Anyone living on a raisin inside that pocket would see the world a little differently than a raisin packed in the crowded crust. That difference is the whole game, because how we measure the universe depends on where we are standing when we measure it. If our address is a hollow pocket, our view could be quietly bent, like reading a map drawn from the bottom of a valley. For decades, cosmologists assumed we sat on average ground, fair and typical. The Counting Project was about to test that comfortable idea directly. And the deeper the team dug into their galaxy counts, the more one uneasy possibility took shape. Our pocket in the bread might be far, far bigger than anyone had dared to guess. The year was 2013. The place, the University of Hawaii and the University of Wisconsin. 3 astronomers sat with a mountain of galaxy data and a simple, stubborn question. How much stuff is really out there near us compared to farther away? Their names were Ryan Keenan, Amy Barger, and Lennox Cowie. Keenan was the young researcher driving the counts. Barger was his advisor. Cowie brought years of experience surveying the deep sky. Together, they set out to weigh the local universe, and they picked a clever way to do it. Most galaxy surveys look in visible light, the same colors your eyes catch. That works, but it has a trap. Bright, active galaxies, bursting with young stars, can fool you. They shine hard and grab attention, which can make a region look richer than it truly is. The team wanted a fairer count, so they turned to near-infrared light. Infrared is the glow of warmth, the light just past red that your eyes cannot see. Old, steady stars pour out infrared, and old stars make up most of a galaxy's true mass. Counting galaxies in infrared is like weighing people by their bones instead of their clothes. You get closer to what is actually there, without the flashy costumes throwing you off. With that fairer measuring stick, they counted galaxies out to greater and greater distances, building a profile of how crowded space is as you move away from us. They expected the crowd to even out, go far enough, and any region should settle toward the cosmic average, the normal fullness of the universe. That is where the numbers turned strange. Close to home, the count ran low. Push farther out, still low. Farther again, and only then did the galaxies thicken toward normal. It was as if we sat at the bottom of a dip that stretched on for an almost unbelievable distance before the universe finally filled back in. The dip was not small or shallow. It kept going for hundreds of millions of light years in every direction they looked, and within it, the galaxies were noticeably thin, as though a huge region around us had been partly hollowed out. They ran the checks. Was it a mistake in the data? A patch of sky blocked by dust? A quirk of their method? One by one, the easy explanations fell away. The dip was real, it was centered near us, and it was enormous. When the shape was fully drawn, the team gave the universe a jolt. Our galaxy, they argued, sits inside one of the largest underdense regions ever measured, a cosmic hollow far bigger than any normal void, with us near the middle of it. Picture measuring the depth of a swimming pool by wading out from the shallow end. You expect the floor to level off. Instead, it keeps dropping, step after step, far past where any pool should end, until you realize you are not in a pool at all. You are standing in a crater. The claim landed with a mix of wonder and doubt. Some scientists were fascinated, others were skeptical, and for good reason. A hollow this large brushed up against the deepest rules of how the universe is supposed to be built. If it was real, it should not be so easy to make. And that raised the next question, the one that would take years to chase down. Exactly how big and exactly how empty was the hole we had woken up inside? Before we measure the hole, it helps to trust the ruler. Because when someone tells you a chunk of the universe is missing its galaxies, your first thought should be a fair one. How could anyone possibly know that? Start with the trick at the heart of it. Galaxies follow a hidden order. Across a big enough stretch of space, they thin out to a steady average. Count a large volume anywhere in the distant universe, and you tend to find a similar number of galaxies packed into it. That steady average is the yardstick. It tells you what a normal, fully stocked region should hold. So astronomers do exactly what it sounds like. They pick a patch of sky, sort out how far away each galaxy is, and tally how many sit inside each shell of distance, like counting how many people live in ring after ring around a city center. Then they compare each ring to the cosmic average. More galaxies than average means a crowded region. Fewer means a hollow. The distance part is the hard part. A galaxy that looks faint might be small and close, or huge and far. To untangle that, astronomers lean on redshift. As the universe expands, it stretches the light traveling across it toward the red end of the rainbow. The more a galaxy's light is stretched, the farther away it generally sits. Redshift becomes a kind of cosmic tape measure. Here is where the infrared choice paid off again. By reading the steady infrared glow of old stars and the redshift of each galaxy, the team could place galaxies at their true distances and count them honestly, ring by ring, without bright show-off galaxies skewing the tally. Now, one survey of one strip of sky could be a fluke. Maybe you just happen to aim at a naturally quiet direction. To rule that out, you have to look all around, in many directions, and check whether the shortage shows up everywhere. If only one patch is empty, you found a local gap. If nearly every direction is low, you might be sitting inside something. That is the test the local hole had to pass, and later surveys pushed it hard, covering the great majority of the sky rather than a single slice. When the counts came back, the shortage did not hide in one corner. It surrounded us. Look left, look right, look up, look down, and the galaxies ran thin in almost every direction before thickening far away. Think of standing in a wide field at dusk while lanterns switch on across the countryside. If the field is dark only toward the north, maybe a storm rolls in from there. If the field is dark in every direction for miles, with distant lanterns glowing only on the far horizon, then the darkness surrounds where you stand. That was the growing verdict. The thinning of galaxies wrapped around us on all sides, which meant we were likely near the heart of it. Still, a careful scientist keeps asking harder questions. How deep is the shortage really? Once you correct for every effect that could fool the count. Could dust, or dim galaxies, or the stretching of redshift itself be quietly hiding matter that is truly there? Those corrections matter enormously, because they decide whether we are talking about a mild dip or a genuine chasm. And when researchers ran them, some of the numbers came back even more extreme than the first announcement suggested. So how big is this thing we live in? Get ready, because the number is hard for a human brain to hold. The local hole stretches roughly 1 billion light-years in every direction from us. That is the radius, the distance from the middle to the edge. Across the full width, side to side, it spans about 2 billion light-years. Light itself, moving at the fastest speed the universe allows, needs 2 billion years to cross the emptiness we are sitting in. Turn that scale into something you can hold. Light circles the entire Earth more than 7 times in a single second. It crosses from the sun to your eyes in about 8 minutes. It reaches the nearest star beyond the sun in 4 years. And to cross our void, that same beam of light must travel for 2 billion years, longer than complex life has existed on this planet. Try shrinking it down. Imagine the whole Milky Way, our galaxy of hundreds of billions of stars, squeezed to the size of a single dinner plate. On that scale, the void around us would be a bubble wider than a large city. Our entire galaxy would be one plate lost inside a hollow the size of a metropolis. Or, picture a football field. If the visible universe were shrunk, so the whole thing fit end to end across the field, our void would still stretch across a large chunk of it. This is a feature you can see on a map of the entire cosmos. A dark bruise centered right where we live. Here is the part that unsettles cosmologists. Voids are common, yes, and they come in ordinary sizes. A normal void might be 100 or 200 million light-years across. Our hollow runs many times larger than that. It is, by the measurements, one of the biggest empty regions ever charted, and we found ourselves living inside it. Think about how odd that is. If you threw a dart at a giant map of the universe, most of the time it would land in an average spot. Landing dead inside a rare, record-breaking hollow would be a strange piece of luck. That strangeness is a clue we will come back to again and again. And the void is wide in time too. Because looking 2 billion light-years out means looking 2 billion years into the past. The walls of our hollow are also a wall of history. The light arriving from the void's distant edge left before our sun was even born. Now, a fair mind pushes back here. 2 billion light-years is a bold claim, and not every astronomer agrees the hollow is quite that large or quite that empty. The exact edge is fuzzy, because the universe fades from thin to normal gradually rather than stopping at a sharp wall. Different surveys draw the boundary in slightly different places, but even the cautious measurements leave us inside something huge, something far larger than the cozy, average neighborhood scientists once assumed we lived in. The debate concerns how extreme the hollow is. Everyone agrees we sit in a big one, and size is only half the shock. A region can be wide yet still nearly full, or narrow yet nearly empty. The truly important question is the second one. Just how much matter is missing from the space around us? And could that missing weight be quietly rewriting what we think we know? Width is one thing, emptiness is another. A giant region could still be nearly full, just a touch below average. So the real question is sharper. How much of the universe is actually missing from around us? The headline figure from the counts is about 20%. Our region holds roughly 1/5 fewer galaxies than a normal patch of the cosmos of the same size. 1 in every 5 galaxies that should be here by the cosmic average simply is not. 20% might sound modest. It is anything but. Spread across a hollow 2 billion light-years wide, a 20% shortage means an astonishing amount of missing matter. We are talking about the mass of many thousands of galaxies worth of material that the average would predict, absent from the space around us. Enough missing weight to tug on the motion of everything inside, and some measurements push the shortage further. When certain researchers corrected the counts for effects that can hide matter, the local region came back even emptier in places, closer to half the normal density rather than 4/5, depending on how you measure. The deepest parts of the hollow may be far quieter than the first announcement suggested. Picture a concert hall built for 10,000 people. A 20% shortage means 2,000 empty seats scattered through the crowd, obvious once you look. A near half shortage means the hall is barely more than half full, with whole rows sitting dark and silent. Now blow that hall up to the size of 2 billion light years, and you start to feel the scale of the quiet. Here is what makes the emptiness matter, beyond the eerie loneliness of it. Matter has gravity. Where matter gathers, its pull is strong. Where matter thins out, the pull is weak. A giant underdense region is, in a real sense, a giant patch of weakened gravity, surrounded by denser walls where the pull is stronger. That imbalance does not sit still. Over billions of years, the stronger gravity of the crowded walls slowly draws matter outward, away from the empty middle and toward the edges. The hollow keeps hollowing itself out. Like water on a tilted table, matter drifts downhill from the thin center toward the thick rim. And if matter is drifting outward all around us, then the galaxies we watch, including the ones we use to measure the universe, carry an extra motion, a quiet outward drift added on top of the calm expansion of space. That hidden drift is the seed of everything strange to come. For now, hold the two facts side by side. Our region is enormous, and it is genuinely underfed, missing something like a fifth to nearly half of its expected matter. Both numbers came from careful counting, cross-checked across most of the sky, and both survived years of skeptical review. Still, a wall of caution remains. Measuring a shortage this large depends on knowing the true cosmic average precisely, and on trusting that no large hidden population of dim galaxies is lurking unseen. If such a hidden crowd exists, the hollow could be shallower than it looks. That possibility keeps the debate alive. Yet, even granting every doubt, the picture holds. We appear to live inside a rare, record-sized region that is markedly emptier than the rest of the universe, which forces an uncomfortable comparison. How does our hollow stack up against the ordinary void scattered everywhere else? The answer is almost embarrassing. Farther still, let us line our hollow up against the competition, because the universe is full of voids, and knowing how ours compares tells you just how unusual our address really is. Ordinary voids, the common empty bubbles woven through the cosmic web, run about 100 to 200 million light-years across. They are already vast beyond human imagining. A single normal void could hold our entire galaxy and its neighbors with room to spare, and light would still need 100 million years to cross it. Now set our hollow beside one of those. By the measurements, our region is around 7 times larger than an average void, 7 times wider in each direction. Since space has 3 dimensions, 7 times wider means the volume balloons enormously, hundreds of times more room than a typical void encloses. Our hollow dwarfs them all. It towers over the ordinary crowd. In fact, by the reckoning of the astronomers who mapped it, this is the largest underdense region we have ever found anywhere in the universe. The largest known, full stop, and we live right inside it, in the middle of it. Sit with how strange that is. Imagine every void in the universe as a lake, and their sizes as ordinary ponds. Ours would be an ocean. Now, imagine you were dropped blindfolded onto the surface of a random world in the cosmos. The overwhelming odds say you would land somewhere average. The chance of opening your eyes to find yourself floating in the single biggest ocean of emptiness ever charted is small. Yet here we are. That low probability is more than a fun fact. It is a genuine headache for the science, and we will feel the full weight of it later. Our leading theory of how the universe grew its structure expects giant hollows this extreme to be rare, almost forbiddingly so. A region this big and this empty should barely exist in the numbers the theory predicts. Finding ourselves parked in the middle of one is like flipping a coin and watching it land on its edge, then doing it again. There are 2 honest ways to react. One is to say, we simply got a rare roll of the cosmic dice. Someone has to live in the biggest void, and it happens to be us. The other is more daring. Maybe such giant hollows are more common than the standard theory allows, which would mean the theory itself is missing something. Both roads lead somewhere uncomfortable. For now, notice what the sheer size has done to the story. We began with a quiet counting project and a mild dip in galaxy numbers. Step by step, that dip has grown into a record-breaking chasm, one so large it strains our best model of the cosmos before we have even asked what it does to our measurements. And the size raises a pointed question about our place inside it. A hollow this big has a middle and an edge, and where we stand within it changes everything about how it would affect us. Sitting near the rim is one story. Sitting near the deep center is a very different one. So which is it? Are we clinging to the wall of this great emptiness or floating in its heart? The answer, it turns out, is stranger and more important than a simple location on a map. Here is a fact that should raise the hair on your neck. Of all the places we could sit within this record-sized hollow, we appear to be parked deep inside it, well away from the crowded walls, out toward the quiet middle. That location is doing a lot of work, so let us be clear about why it matters. A giant, underdense region affects an observer differently, depending on where that observer stands. Near the dense rim, the pull of the surrounding walls comes mostly from one side, and the effects on your measurements would look lopsided, strong in one direction and weak in the other. Deep in the middle, the walls surround you on all sides, and their outward pull becomes roughly even in every direction you look. Even in every direction is exactly what the galaxy counts show. The thinning of galaxies wraps around us like a shell. Look toward any part of the sky, and the region runs low before filling in far away. That symmetry is a fingerprint. It points to us being near the center of the hollow, ringed by its distant walls. Picture standing in the middle of an empty stadium. The seats rise around you on every side, equally far away. Walk to the very center of the field and look out. Left, right, forward, back. The crowd sits at the same distance all around. That balanced view is what you get from the middle. Stand near one goal line instead, and the stadium looks crowded in front and open behind. Our sky looks like the middle of the stadium. This changes the whole flavor of the mystery. If we clung to the rim, the hollow would tilt our view, easy to spot and easy to correct. Sitting in the heart is subtler and, in a way, more dangerous for anyone trying to measure the universe. Because from the center, the outward drift of matter would pull galaxies away from us fairly evenly on all sides. And evenly on all sides is precisely what expansion looks like. When the universe stretches, everything rushes away from us in every direction at once. So if the walls of our hollow are also pulling nearby galaxies outward in every direction, that extra motion would blend in perfectly with the true expansion, hiding in plain sight. From inside the center, you might struggle to tell the two apart without very careful work. That is the trap taking shape. A giant hollow, with us near its middle, quietly adding outward motion that mimics the very thing we are trying to measure. If real, it would mean our front row seat to the universe comes with a built-in distortion we cannot simply look past. Now, a careful voice pushes back, and rightly. Claiming we sit near the center of the largest known void is a bold, almost suspiciously tidy statement. Are we really so specially placed? Or is the apparent symmetry partly an accident of which directions we have surveyed best? These are fair doubts, and honest researchers raise them. Yet the balance of the evidence keeps pointing the same way. The shortage looks roughly even around us, which places us somewhere near the heart of the hollow. Still, near the center leaves room for a small offset, and that distinction, whether we sit exactly in the middle or a little off to one side, hides a clue that some scientists think we can actually detect. So, are we sitting at the exact bullseye of this hollow, or slightly off to one side? The question sounds like a tiny detail. It is anything but, and here is why. If we sat at the perfect center of a perfectly round void, the outward pull of the walls would be flawlessly even, every direction identical. The extra motion of nearby galaxies would spread out in a smooth, balanced sphere around us, clean and symmetrical. But almost nothing in the universe is perfect. Real voids are lumpy, with walls closer on one side than the other. And the odds of us landing on the precise mathematical center of a 2 billion light-year hollow are tiny. Far more likely, we sit somewhere near the middle, but a little off, closer to one wall than the rest. That small offset leaves a signature. If we are nearer to one side of the hollow, the closer wall pulls a bit harder from that direction, and the far wall pulls a bit softer from the other. The outward drift of galaxies would no longer be perfectly even. It would tilt ever so slightly, stronger toward one part of the sky and weaker toward the opposite part. Recent studies have chased exactly that tilt. Rather than assume we sit dead center, researchers modeled a hollow with us, placed a little off to one side, and then asked what pattern of galaxy motion that would create. Their work suggests we likely do sit within a few 100 million light-years of the center, close in cosmic terms, though probably not exactly on it. Why does a mere offset matter so much? Because it turns a vague idea into a testable one. A perfectly centered void makes a simple prediction. An off-center void makes a richer prediction, a specific lopsided pattern of motion that scientists can go looking for in the real sky. If that predicted tilt shows up in the data, it becomes strong support for the whole picture. If it fails to appear, the picture is in trouble. Think of dropping a stone into a round pond. Drop it dead center, and the ripples spread out in perfect rings. Drop it off to one side, and the ripples reach the near bank first, the far bank later, in a pattern you can predict from exactly where the stone landed. Our motion through the cosmos may carry ripples like that, and they're shaping codes where we sit inside the hollow. Astronomers have begun measuring the large-scale flows of galaxies around us, the great streaming motions of thousands of galaxies at once, to test whether they match what an off-center hollow would produce. Some of those flows do line up in a preferred direction, which fits the idea of a slightly lopsided void tugging us along. Others are harder to square with the models, and the argument continues. That tension is healthy. It means the void idea sticks its neck out. It predicts specific motions in specific directions, and it can be proven wrong. That is what separates a real scientific claim from a comfortable tale. For now, the working picture is this. We float somewhere near the heart of the largest known hollow in the universe, likely just off its true center, carried along by the slow outward drift of a region that has been emptying itself for billions of years. But the strangest thing is that the hints of this hollow were spotted long before the famous counts of 2013. Someone had already glimpsed the missing galaxies and been met with disbelief. Long before 2013, the universe had been dropping hints that our neighborhood was strangely quiet. People noticed. Most of them were waved off. Go back to around 1990. Astronomers mapping galaxies in visible light kept finding fewer of them nearby than the cosmic average predicted. A shortage in the local counts. It was faint and easy to blame on incomplete surveys or patchy data, so it lingered as a curiosity rather than a crisis. Through the 1990s and into the 2000s, other teams took fresh looks, some in infrared light, and the same odd shortage kept turning up. Region after region came back a little emptier than it should be. Each study on its own was arguable. Stacked together, they whispered the same thing. Our local patch was underfed. Then came a sharper warning. A veteran astronomer named Igor Karachintsev studied the galaxies in our immediate cosmic backyard, a sphere reaching out roughly 150 million light-years around us. He tallied the matter inside and compared it to what the standard model of cosmology predicts a region that size should contain. The result was jarring. The density he measured came in several times lower than expected, by a factor of 3 to 4 in his reckoning. In other words, our backyard held only a fraction of the matter the theory demanded. That is a severe shortfall, and it came from a careful, respected researcher. Picture ordering a moving truck packed to hold the belongings of 4 families, then opening the doors to find the furniture of barely one. You would not shrug, you would demand to know where everything went. Karachintsev was, in effect, opening that truck and finding it mostly empty. Still, the wider field hesitated. A shortage in one sphere could be a fluke, Maybe our little corner just happened to be quiet, a small local dip with no deep meaning. To claim something bigger, you needed to show the emptiness extended much farther out, in a fair count across most of the sky. That is exactly the gap the 2013 team stepped in to fill, when they extended the counts to far greater distances, using the fairer infrared measuring stick and covering wide stretches of sky. The local dip did not close. It stretched on and on, revealing that the shortage Karachentsev and others had glimpsed nearby was the inner slope of something enormous. The whispers had been early views of the same giant hollow, seen from too close to grasp its true size. There is a lesson buried here, and it is a human one. The signal had been there for decades. Researchers dismissed it again and again, partly because it clashed with a comfortable assumption, the belief that we live in an ordinary, average place. Scientists are people, and people resist news that shakes the foundations. It took better instruments, wider surveys, and a stubborn team to force the idea into the open. Even now, the debate continues, and that is proper. Extraordinary claims deserve hard scrutiny, and a hollow this large is about as extraordinary as it gets. But the early hints, once brushed aside, now read like a trail of footprints, leading straight to the edge of something vast. The hollow had earned attention, and with attention came a flood of names. Different scientists, coming at it from different angles, each called it something of their own, and the tangle of names hints at just how many corners of astronomy this one region touches. By now, this giant emptiness has collected almost as many names as a wanted outlaw. Each one comes from a different group of scientists, and each hints at a different piece of the puzzle. The most formal name honors the three astronomers who measured it in 2013, Keenan, Barger, and Cowie. Their initials became a label used in research papers, a tidy tag for the underdense region they mapped. When cosmologists write about it, that is usually the name they reach for. But long before that, British astronomers who had been finding the local shortage in their own surveys called it something plainer and gloomier: the local hole. It is a fitting phrase. It captures the simple, unsettling truth that right where we live, the universe has a hole in it. Others prefer the grander-sounding supervoid. There is a reason for the prefix. Astronomers reserve the word supervoid for the truly enormous hollows, the ones larger than about 300 million light-years across. Our region blows past that threshold many times over, so it earns the title easily. Calling it a supervoid signals that this is no ordinary gap. It is a heavyweight. Then there is the nickname that hints at the real drama to come: the Hubble bubble. That playful name links the hollow to a deep crisis in cosmology, one built around the work of Edwin Hubble, who first showed that the universe is expanding. The nickname suggests that our bubble of emptiness might be meddling with our measurements of that very expansion. Hold on to that name. It is a signpost pointing at the heart of this story. 4 names, then, for one region: the formal initials, the blunt local hole, the grand supervoid, and the loaded Hubble bubble. They are all the same place, the same 2 billion light-year stretch of quiet with us near its middle. The variety of names is itself a clue. It tells you how many different fields of astronomy have bumped into this thing from their own directions. Galaxy counters found it by tallying too few galaxies. Motion mappers found hints of it by watching galaxies stream in unexpected ways. And expansion measurers ran into it while wrestling with a stubborn disagreement about how fast the universe is growing. When several independent groups, using entirely different methods, keep circling the same region, that is the kind of overlap that makes scientists take an idea seriously. Think of blind investigators each feeling a different part of the same huge animal in the dark. One touches a wide flank and calls it a wall. Another touches emptiness and calls it a hole. Another feels a strange tug and calls it a current. Only when they compare notes does the full creature take shape. And it turns out they were all describing one enormous thing. That is roughly where the science stands. Many teams, many names, converging on a single giant hollow that seems to touch counting, motion, and the expansion of the cosmos all at once. And it is bigger, in reach, than even those names suggest, because the hollow does more than hold scattered galaxies. It swallows entire structures we once thought of as our grand cosmic home, including a supercluster so vast it was only mapped in the last decade. That structure has a name of its own, and learning that it too sits trapped inside the emptiness reshapes how we picture our place in the universe. To feel how much this hollow contains, you have to meet our true cosmic home. Its name is Laniakea, and it is far larger than most people ever realize. For a long time, we knew the Milky Way belonged to a small cluster of galaxies called the Local Group, and that the Local Group sat near a bigger crowd called the Virgo Cluster. That seemed like the extent of our address. Then, about a decade ago, astronomers mapped the motions of thousands of galaxies around us and found something breathtaking. All those galaxies, across an immense span of space, were flowing together, drawn along shared streams toward a common region. By tracing which galaxies moved as one great connected flow, the researchers outlined a single colossal structure and named it Laniakea, a Hawaiian phrase meaning immense heaven. The name fits. Laniakea holds an estimated 100,000 galaxies, each one a swirl of hundreds of billions of stars in its own right. It stretches more than 500 million light-years across. Our Milky Way, for all its grandeur, is a single modest thread near the outer parts of this supercluster, one galaxy among 100,000, riding the flow. For a while, Laniakea felt like the ultimate home address, the biggest structure we belonged to, our place finally mapped at the grandest scale. And then came the twist. This titanic supercluster, 100,000 galaxies strong, sits inside the hollow. Laniakea itself is largely swallowed by the local emptiness. Sit with that nesting for a moment. Earth orbits the Sun. The Sun is one star among hundreds of billions in the Milky Way. The Milky Way is one galaxy among 100,000 in Laniakea. And Laniakea, immense heaven, is itself adrift inside a hollow so vast it dwarfs the supercluster many times over. Layer upon layer, each one shrinking us further. Here is the piece that ties it back to the mystery. Laniakea was mapped by tracking motion, by watching how galaxies stream, and those streams carry more than the calm expansion of the universe. Whole rivers of galaxies are flowing in shared directions, tugged by the uneven pull of matter around them. An emptying hollow would produce exactly this kind of large-scale streaming. If matter is draining outward from the underdense middle toward the denser walls, then galaxies across our region, including our own, would be carried along in great coordinated flows. The very motions that revealed Laniakea may be partly the signature of the hollow itself, quietly steering everything within it. Picture a slow, wide whirlpool in a river. Leaves, twigs, and foam all drift together, carried by the same current, tracing the shape of the flow. Laniakea is a bit like that pattern of drifting things, and the hollow may be part of the current beneath it, guiding the drift on a scale almost beyond comprehension. So, our home is 100,000 galaxies in motion, nested inside a record-breaking emptiness, all of it slowly streaming. And that motion is the bridge to the deepest part of this story. Because if our entire region is drifting, then the galaxies we rely on to measure the universe are drifting too. Their light carries not only the stretch of cosmic expansion, but also the extra push of that drift. Which brings us to the crack that this whole mystery may explain. A crack running right through modern cosmology, centered on a single number that refuses to agree with itself. There is a number in cosmology that has broken the peace. Two respected teams, using two trusted methods, measure it carefully. They get two different answers, and no matter how many times they check, the answers refuse to meet. The number describes how fast the universe is expanding. Ever since Edwin Hubble showed, almost a century ago, that distant galaxies are rushing away from us, cosmologists have chased a single value for the rate of that expansion. Nail it down, and you can wind the cosmic clock backward to the Big Bang and forward to the universe's fate. It is one of the most important numbers in all of science. For decades, measuring it was so hard that the results came with huge uncertainty, and everyone's answers overlapped in a comfortable fog. As long as the error bars were wide, disagreement could hide inside them. Then the instruments got better, much better. The fog burned away, the uncertainties shrank, and something alarming happened. As each method grew sharper, the two answers grew farther apart. One method reads the expansion rate from the ancient light of the early universe. It arrives at a lower value. The other method reads it from nearby galaxies in the universe today. It arrives at a higher value. Both rest on exquisite care. Both have survived repeated checks, and the gap between them has refused to close. Scientists gave this standoff a name: the Hubble tension. Tension is the right word. It is the strain of two solid measurements pulling in opposite directions, each backed by strong evidence, neither willing to yield. For years now, it has been one of the loudest, most stubborn problems in physics. Why does a disagreement about one number matter so much? Because that number is woven into everything. It sets the size of the observable universe, its age, and the balance of what it is made of. If the early universe and the nearby universe genuinely disagree about the expansion rate, then something in our understanding is broken. Either a measurement is fooling us, or the laws we thought governed the cosmos are incomplete. Picture two master clockmakers handed the same clock. One measures its ticking by listening to the gears deep inside. The other measures it by watching the hands sweep the face. They should agree perfectly. Instead, one insists the clock runs slow, and the other insists it runs fast, and both have checked their work 100 times. Either the clock is stranger than it looks, or one of them is being deceived by something they cannot see. That is the crisis in miniature, and it is where our hollow steps onto the stage. Because one of those two measurements, the one taken from nearby galaxies, is made entirely from inside our region, inside the emptiness, inside the drift. If the galaxies we measure are being carried outward by the pull of an emptying hollow, then the nearby method might be reading a speed that is partly real expansion and partly local drift, mixed together. The clockmaker watching the hands might be standing on a moving floor. That is the possibility that turns a giant void from a curiosity into a suspect. Maybe the hollow is the very reason our two measurements refuse to agree. To see how that could work, we first have to understand the two clockmakers themselves. How do you measure the expansion of the entire universe in two completely different ways? The first method reaches all the way back to the oldest light there is. How do you even measure the speed of the whole universe expanding? You cannot lay a ruler across the cosmos. So scientists found two brilliant, completely separate ways to do it, and the split between them is the key to everything. The first way looks backward in time to the infancy of the universe. Shortly after the Big Bang, the cosmos was a blazing fog of hot gas. As it expanded and cooled, that fog cleared and released a flash of light that has been traveling ever since. That ancient glow still washes over us today, stretched by billions of years of expansion into a faint hum of radiation filling all the sky. Locked inside that ancient light is a detailed snapshot of the young universe, its temperature and its lumps and ripples frozen in place. By reading that snapshot and applying our physics, scientists can calculate how fast the universe should be expanding now. This is the early universe method. It reaches back to the beginning and works forward. Its answer comes out on the lower side. The second way looks at the universe today, right around us. It builds a chain of distance measurements out into nearby space, rung by rung, using objects whose true brightness we understand. By comparing how bright these objects truly are to how bright they appear, astronomers work out how far away they sit. Then they check how much the expanding universe has stretched their light. Distance on one side, stretch on the other, and out pops the expansion rate. This is the nearby method. and its answer comes out on the higher side. Two methods, two directions in time, two philosophies. One extrapolates forward from the dawn of the cosmos. The other measures directly in our own backyard. In a healthy universe, they should land on the same number. That would be the triumph, early and late agreeing, the whole story hanging together. Instead, they disagree, and the disagreement has held firm as both methods sharpened. That is what makes it so serious. A single sloppy measurement could be dismissed, but two careful, independent methods, refined for years by rival teams, both confident, both landing in different places, that is a puzzle you cannot wave away. Think of measuring the height of a mountain two ways. One team calculates it from the pressure of the air at the summit using known physics. Another team walks up with survey gear and measures it directly, step by step. If both are careful and they get different heights, you do not just pick a favorite. You start to suspect that something about the mountain, or the air, or the ground itself is not what you assumed. Now here is the crucial detail for our story. The early universe method reads from light that comes from far, far beyond our hollow, light that crossed most of the cosmos to reach us. It samples the universe as a whole. The nearby method, by contrast, is measured entirely from inside our region, using galaxies that sit within the drifting emptiness. That difference is everything. If our hollow adds a hidden outward drift to nearby galaxies, it would inflate only the nearby measurement, the one taken from inside. The early universe number, sampling the whole cosmos from beyond the hollow, would stay clean. So, which number is which? Let us start with the deep one, the reading taken from the oldest light in existence, and see exactly what value it gives. The oldest light in the universe has a story to tell, and it comes with a number. That number is about 67. Rewind to roughly 400,000 years after the Big Bang. Before that moment, the universe was too hot and too dense for light to travel freely. It was a glowing fog, so thick that light bounced endlessly between particles and could not escape, like sunlight trapped inside a cloud. The whole cosmos was an opaque, blazing haze. Then the universe expanded and cooled past a tipping point. The fog cleared almost all at once. Particles joined into stable atoms, and suddenly light could stream across space unobstructed. That freed light has been flying ever since, for more than 13 billion years, stretched longer and longer by the expansion of space, until it became a faint whisper of radiation that fills the entire sky in every direction. We can detect that whisper today with sensitive instruments. It is the afterglow of creation itself, the single oldest thing we can observe, and it is astonishingly uniform, nearly the same temperature everywhere, a smooth wash of ancient warmth, but hidden inside that smoothness are tiny variations, faint hot and cold patches, ripples frozen into the light from the infant universe. Those ripples are pure gold for science. Their sizes and spacing encode the exact conditions of the young cosmos. How much matter it held, how fast it was flying apart, what it was made of. Reading the pattern of ripples is like reading a detailed blueprint of the universe when it was newly born. From that blueprint, scientists run the known laws of physics forward across billions of years to predict how fast the universe should be expanding today. The calculation is careful, the data is exquisite, and the answer is remarkably precise. The expansion rate that comes out sits right around 67, in the units cosmologists use for the growth of space. The great strength of this number is where it comes from. It is anchored in the earliest, cleanest snapshot of the universe, from light that crossed almost the entire cosmos to reach us. It samples everything, the whole vast sweep of space, far beyond any local quirk in our own neighborhood. In that sense, it is a measurement of the universe as a whole, and that is exactly why it matters for our mystery. This ancient number sees the big picture. Light from the early universe travels to us from distances far greater than the width of our hollow, passing through the average density of the entire cosmos on the way. Whatever strangeness surrounds our local address, this measurement mostly looks past it. So think of the 67 as the honest reading of the whole universe, taken from the outside in, from the oldest evidence we have. If the cosmos has a single true expansion rate, many scientists suspect this deep measurement is close to it, because it is the least tangled up in local effects, which sets up the confrontation. If 67 is the true, universe-wide expansion rate, then any other measurement that disagrees needs an explanation. And there is another measurement, made much closer to home, that stubbornly refuses to match it. That nearby number is built from exploding stars and pulsing suns in our own backyard, and it comes out noticeably higher, a difference that has driven cosmologists to the edge of rewriting physics. Now for the other clockmaker. This one works close to home, using stars we can watch tonight, and it gets a higher answer, about 73. The trick is building a ladder of distances, one careful rung at a time. To measure how fast the universe expands, you need to know two things about faraway galaxies: how far away they are, and how much the expansion has stretched their light. The stretching is easy to read. The distance is the hard part, and it demands objects whose true brightness we already know. The first rung uses a special kind of star called a Cepheid. These stars pulse, swelling and shrinking in a steady rhythm, and their rhythm reveals their true brightness. A Cepheid that pulses slowly is genuinely bright. One that pulses fast is dimmer. Read the beat, and you know exactly how much light the star truly pours out. Compare that to how faint it looks from Earth, and its distance falls right out. Think of it like a lighthouse whose real power you can read from the speed of its flashes. But Cepheids fade from view at great distances, so astronomers add a brighter rung when certain white dwarf stars explode as a particular type of supernova. They blaze with a brightness that is remarkably consistent, one exploding star briefly outshining an entire galaxy. Because their true brightness is so reliable, these explosions work as beacons visible across enormous stretches of space. The teams calibrate the exploding stars using the nearby Cepheids, then use those explosions to reach far out into the universe, measuring distances rung by rung. At each step, they also read how much the expansion has stretched the light. Put the distances and the stretches together, and out comes the expansion rate. The answer lands around 73, clearly above the 67 read from ancient light. For a long time, that gap could be blamed on messy measurements. But the nearby teams have refined this ladder relentlessly, checking each rung, hunting for hidden errors, tightening every step, and the more they tightened it, the more stubbornly the number held near 73. The gap hardened rather than closing. Here is the detail that ties it straight to our hollow. Every rung of this ladder sits inside our local region. The Cepheids, the exploding stars, the nearby galaxies, all of them lie within the drifting emptiness we call home. This measurement is taken entirely from the inside. Now, recall what an emptying hollow does. It pulls nearby galaxies outward toward its denser walls, adding a small extra motion on top of the true cosmic expansion. If the galaxies used in this ladder carry that extra outward drift, their light would look a little more stretched than pure expansion alone would make it, and more stretch reads as faster expansion. So the 73 might be telling a mixed story. Part true expansion, part local drift, blended together and mistaken for a single number. The clockmaker, measuring the hands of the clock, may be standing on a slowly moving floor, reading a speed that is partly the clock and partly the floor. That is the heart of the void solution to the great disagreement. But before we chase how the hollow could bend the number, one question demands an answer. The gap between 67 and 73 looks small, 6 units. Why do scientists treat such a tiny difference as a full-blown crisis? 67 and 73. The gap is only about 6. It looks tiny, the kind of difference you might shrug off. Yet cosmologists lose sleep over it. To see why, you have to understand what makes a difference in science truly matter. A measurement is only as meaningful as its uncertainty. Every reading comes with a margin, a range around it where the true value probably lies. If two measurements have wide, overlapping margins, a gap between them means little. They might really be the same, and the difference is just noise. But if two measurements have tiny, tight margins and still refuse to overlap, then the gap is real, and it demands an explanation. That is exactly what has happened here. Both the ancient light number and the nearby star number have been measured with extraordinary precision. Their margins have shrunk to slivers, and even with those slivers, the two numbers sit far apart, with a wide gulf of impossibility between where one ends and the other begins. Scientists measure the seriousness of such a gap in a unit that counts how unlikely it is to be a fluke. The higher the count, the smaller the chance that random error is fooling everyone. By tradition, once a result crosses a certain threshold, physicists call it a genuine discovery rather than a coincidence. That threshold is famous, the same bar used to confirm major particle discoveries. The Hubble tension blew past that bar and kept going. The disagreement between the two expansion numbers now sits at a level where the odds of it being a random accident are staggeringly small, less than 1 in a million. Something real is causing the split, rather than sloppy work or bad luck. Picture two archers, each firing at the same target from opposite sides. Early on, both are shaky, their arrows scattered wide, and their groupings overlap in the middle, so you cannot tell them apart. Then, both archers become experts. Their arrows cluster into tight little knots. But now the two knots land in clearly different spots, with clean, empty space between them. Tight aim and separate targets mean the difference is no accident. The two archers really are hitting different marks. That is where cosmology stands. Two expert measurements, each landing in a tight cluster, and the clusters sit apart with confidence that borders on certainty. The universe is telling us that the early cosmos and the nearby cosmos disagree about how fast space is stretching, and it is telling us loudly. So, the scientists face a hard fork, and neither path is comfortable. One path says a hidden error still lurks in one of the measurements, some subtle effect no one has caught. The other path says both measurements are right, and our understanding of the universe itself is missing a piece. Either way, something important is wrong. This is why a giant hollow around us is such a tempting suspect. It offers a way out that spares the deepest laws of physics. If our nearby measurement is inflated by the outward drift of an emptying void, then the true expansion rate could be the lower number all along, and the higher one is a local illusion. The crisis would dissolve, explained by our unusual address. It is an elegant idea, but elegance is not proof. For the hollow to truly solve the tension, it has to do more than sound clever. It has to work in the details, in the actual physics of how emptiness bends motion, and that is exactly where the real test begins. The bold idea at the center of this story sounds almost like cheating. What if the universe expands at one steady rate everywhere, and the faster number we read nearby is simply a trick played on us by the emptiness we live in? Here is the thinking. The nearby measurement is honest. The teams building the distance ladder are careful, their stars are reliable, their math is sound. The trouble may lie in the thing being measured. If the galaxies in our backyard carry a hidden extra motion, then our instruments faithfully record a speed that is partly real and partly illusion. The tool works fine. The world it is measuring is tilted. That is a very different claim from saying someone made a mistake. A mistake you fix by checking your work. This is subtler. Every reading could be correct, every rung of the ladder solid, and the final number could still be wrong for the whole universe, because it was taken from a strange spot. Cosmologists call the comfortable assumption behind all this the idea that the universe looks roughly the same everywhere. On the largest scales, one big region should resemble any other. Build your measurements on that footing, and a reading taken here should match a reading taken anywhere. The giant hollow attacks that footing directly. If we live somewhere unusual, then here is a bad place to measure the average. Picture trying to learn the average temperature of a whole country by reading a thermometer in your own kitchen. If your kitchen happens to sit next to a roaring oven, your reading runs hot, no matter how good the thermometer is. You would swear the country was warmer than it truly is, fooled by your own address. The Hollow could be doing that to our expansion measurement, running the number hot. The beauty of this idea is what it rescues. If the nearby number is inflated by our location, then the true, universe-wide expansion rate could be the lower value read from ancient light all along. The great disagreement would melt away, and it would melt without breaking the deepest laws of physics, without inventing exotic new forces or rewriting how the cosmos works. The fix would be our unusual home, rather than a flaw in reality itself. That is a tempting prize. The Hubble tension has driven some scientists to propose wild new ingredients for the universe: strange energies and unseen particles. The void offers a calmer escape. Keep the physics. Change the assumption that we live in an average place. Tempting, though, is a warning as much as a promise. An idea that neatly saves everything can seduce you into believing it before it earns belief. Scientists know this danger well. So, the void solution cannot simply sound elegant. It has to survive hard, specific tests. It has to predict things we can go out and check, and match them. And to know what to check, we first have to understand exactly how a region of nothing could push galaxies around at all. Emptiness has no engine, no rockets, no hands to shove things. So how does a hole in the universe reach out and add motion to the galaxies inside it? The answer lies in the strangest property of empty space. A hollow, it turns out, pulls. And to see how nothing can tug on something, we have to watch matter slide downhill in a landscape made of gravity. So how does a region of nothing shove galaxies around? Emptiness has no engine and no hands. The secret is that in a universe ruled by gravity, empty space behaves like the top of a hill. Start with a simple truth about gravity. Matter pulls on matter. Where matter piles up, its pull is strong. Where matter thins out, the pull is weak. Now think about our hollow. In the middle sits the underdense region, light on matter. Around it stand the walls, heavy with galaxies. So the strong pull is on the outside, and the weak pull is in the middle. That imbalance creates a gentle but relentless outward tug. A galaxy sitting inside the hollow feels the heavy walls pulling it toward them, and feels almost nothing pulling it back toward the empty center. Over time, that galaxy drifts outward, away from the middle, toward the crowded rim. Every galaxy in the hollow feels the same one-way tug, so the whole region slowly empties itself, matter draining from the center toward the walls. Here is the cleanest way to picture it. Imagine a wide, shallow bowl turned upside down, so its surface forms a smooth hill. Set a marble anywhere on that hill, and it rolls downhill, away from the top. Our hollow is like the top of a gravity hill. Galaxies inside it are the marbles, and they roll outward, away from the empty summit, toward the dense valleys of the walls all around. The tug on any single galaxy is tiny. Over a human lifetime, or even over all of recorded history, you would never notice it. But the universe has had billions of years to let this drift build up, and space is patient. Across those billions of years, the steady outward pull adds up into real, measurable motion. The hollow has been quietly draining itself for most of the age of the cosmos. And this is where the drift meets our measurements. Remember, the nearby expansion number is read from galaxies inside this hollow. Galaxies that are all rolling gently outward. When astronomers point at a nearby galaxy on the far side of the hollow from us and measure how fast it recedes, they catch two motions at once: the true expansion of the universe, plus the extra outward drift of that galaxy sliding down the gravity hill, away from the center we both share. Those two motions blend together in the stretched light. The instrument cannot separate them. It reads a single speed, and that speed is a little too fast, puffed up by the drift. The galaxy looks like it is fleeing faster than expansion alone would carry it, because it is genuinely moving faster, pushed by the emptiness. This is the engine of the whole void solution. A hole in the universe, acting like a hill, giving every galaxy inside a slow shove outward, and that shove sneaking into our expansion measurement and inflating it. Scientists have a name for this extra, non-expansion motion. They call it peculiar velocity, and it turns up all over the cosmos, wherever matter clumps unevenly. To trust the void idea, we need to understand this hidden motion clearly, because it is the ghost riding inside every reading we take. And peculiar velocity has a habit of pretending to be something it is not. The universe is full of motion that has nothing to do with its expansion. Scientists call it peculiar velocity, and it is the ghost hiding inside nearly every measurement we take of distant galaxies. Here is the distinction that matters. When we say the universe is expanding, we mean that space itself is stretching, carrying galaxies apart the way dots on a balloon spread as you blow it up. The dots do not crawl across the rubber. The rubber grows beneath them. That is expansion, smooth and universal, carrying everything away from everything else. But galaxies also move on their own, across space, pushed by the gravity of their neighbors. A galaxy falling toward a massive cluster is moving through space, not just being carried by it. That personal motion, layered on top of the smooth expansion, is peculiar velocity. The word peculiar here means particular to that galaxy, its own private drift. Every galaxy has some of it. Our own Milky Way is racing through space at hundreds of miles every second, pulled by the uneven spread of matter around us. That is peculiar velocity, and it is completely separate from the expansion of the universe. We are both being carried apart by growing space and swimming through it under gravity's pull. The problem is that our instruments cannot tell the two motions apart. When we measure how much a galaxy's light is stretched, we get one combined number, the sum of the smooth expansion, plus that galaxy's private drift. The stretch does not come with a label saying how much was expansion and how much was peculiar velocity. They arrive fused together. For a single galaxy, this is a manageable nuisance. Personal drifts point in random directions, so if you average enough galaxies, the private motions tend to cancel out. One galaxy drifts left, another drifts right, and across a big enough crowd, the drifts wash away, leaving the clean expansion behind. That averaging is how astronomers normally beat the ghost. The trap springs when the drifts do not cancel. If some large force pushes many galaxies in the same direction, their peculiar velocities line up instead of cancelling, and no amount of averaging removes them. A shared, coordinated drift survives the average and sneaks straight into the final number. Picture a crowd of people milling in a plaza. If everyone wanders randomly, the average position of the crowd stays put, their motions cancelling. But tilt the plaza slightly, and everyone drifts downhill together. Now the whole crowd shifts as one, and averaging their motion no longer gives zero. It gives the slide. That is precisely what a giant hollow would do. It tilts the plaza. Instead of random drifts that cancel, it gives galaxies across our whole region a shared outward push, all rolling down the same gravity hill in a coordinated flow. Those aligned peculiar velocities do not average away. They persist, and they contaminate the expansion rate we measure from inside. So the void solution rests on turning peculiar velocity from a nuisance that cancels into a bias that stays. A coordinated, region-wide drift that masquerades as extra expansion and puffs up our nearby number, which raises the sharp question: why does a coordinated outward drift make the universe look like it is expanding faster rather than slower or sideways? The answer has to do with where we sit, and it reveals why our central spot in the hollow is the perfect setup for an illusion. Why does sitting inside a draining hollow make the universe look like it is racing outward faster than it really is? The answer comes from our address, right near the center. Recall where we are. We float near the middle of the hollow, ringed on all sides by the dense walls. And recall the drift. Every galaxy in the hollow rolls slowly outward, away from the center toward those walls. Now put those two facts together and look out from our central spot. A galaxy sitting between us and the far wall, on one side of the sky. is drifting away from the center, which means it is drifting away from us. A galaxy on the opposite side of the sky is also drifting toward its nearest wall, again away from the center, again away from us. Look in any direction, and the nearby galaxies are sliding outward, which from our central seat means sliding away from us in every direction at once. That phrase should sound familiar. Away from us in every direction is the exact signature of cosmic expansion. When space stretches, everything recedes from us on all sides. So the outward drift of a hollow, seen from its center, perfectly mimics expansion. It adds a little extra recession to every nearby galaxy, in every direction, layered right on top of the real thing. This is why our central location is the perfect trap. If we sat off near one wall, the drift would look lopsided, galaxies fleeing fast on one side and slow on the other, an obvious oddity we could catch and correct. From the center, the drift is even, symmetric, seamless. It hides inside the expansion because it wears the same shape. Picture standing in the middle of a huge crowd on an ice rink, everyone slowly sliding outward toward the walls. From your spot in the center, every person drifts away from you, in every direction, smoothly and evenly. You might swear the whole rink was growing beneath your feet, when really the crowd is just sliding outward around your central position. The even, all directions retreat fools you into seeing expansion where there is drift. So the hollow does not merely add random noise, it adds a bias with a specific flavor, an extra outward flow that looks exactly like faster expansion when measured from the middle. That is why the nearby number comes out high. Our galaxies are genuinely receding a touch faster than pure cosmic expansion would carry them, boosted by the outward roll of the emptiness. And we read that boost as speed. By careful estimates, this effect could inflate the local expansion reading by around 10%. 10% may sound small, yet it is almost exactly the size of the gap between the two rival numbers. The higher nearby value sits roughly 10% above the deeper cosmic one. The hollow, if it works as described, could account for the entire disagreement. The tension would dissolve into an illusion of address. That neat match is thrilling and suspicious in equal measure. When a single idea explains a stubborn mystery with the right size effect in the right direction, scientists lean in, then immediately try to break it. To test it properly, physicists needed a way to put the hollow into their equations, to calculate exactly how much drift it should produce, and they found a clever mathematical trick, treating the emptiness as though it were a strange kind of mass with a negative sign. To test the hollow with real math, physicists needed a way to put emptiness into their equations. They found a clever trick. You can treat a void as if it were a lump of negative mass sitting in an otherwise smooth universe. The idea sounds bizarre at first, since there is no such thing as negative mass in the real universe. But it works as a bookkeeping tool. Imagine the whole cosmos filled evenly with matter at the average density. That smooth background is easy to handle with the standard equations. Now, to make a void, you subtract some matter from one region. Subtracting matter from a uniform background is mathematically the same as adding a patch of negative mass on top of it. Why bother with such a strange picture? Because it turns a messy problem into a familiar one. Scientists know exactly how ordinary mass pulls on things. It attracts. A lump of positive mass draws nearby matter inward toward itself. So a lump of negative mass, being the mirror image, does the opposite. It pushes nearby matter away, repelling it outward. That repelling push is precisely the outward drift we have been describing. The hollow, treated as concentrated negative mass, shoves galaxies away from its center, out toward the walls. The strange trick reproduces the exact behavior we expect, and now it comes wrapped in equations physicists can actually solve. Think of it like accounting for a debt. If a bank account should hold $1,000 but only holds $800, you can describe the shortfall as owning $800 or as owning $1,000 while carrying a $200 debt. The debt is not a real pile of anti-money. It is a bookkeeping way to track what is missing. Negative mass is the same. It is a debt of matter, a way to track the shortfall, and it behaves in the math like a source of outward push. With this tool in hand, scientists could finally calculate the details. Feed in the size of the hollow, feed in how empty it is, feed in where we sit inside it, and the equations spit out how fast the galaxies should be drifting and how much the local expansion reading would be inflated as a result. The vague story became a machine that produces numbers. When researchers ran that machine with the measured size and depth of our hollow, the results were striking. The predicted outward drift came out large enough, and in the right direction, to boost the nearby expansion number by close to the amount needed to erase the tension. The bookkeeping trick, applied to the real hollow, pointed straight at the answer scientists were hoping for. That was a genuine milestone. It moved the void idea from hand-waving to hard prediction. Now there was a concrete model, tied to real measurements, making specific claims about motion and expansion that other scientists could test against fresh data. But a model that fits the thing it was built to explain is only the beginning. The real power of a scientific idea is whether it predicts something new, something you did not put in by hand. And the hollow does make such a prediction, one rooted in a simple, almost frustrating fact about how far our measurements can reach. We are stuck inside this thing. And that limit, it turns out, is both the reason the illusion works and the key to catching it. Here is a frustrating truth that also happens to be the key to the whole puzzle. When we measure the nearby expansion rate, we almost never reach far enough to climb out of the hollow. We are stuck measuring from inside. There is a solid reason astronomers stay close for this particular measurement. The expansion rate of the universe has changed over cosmic history, speeding up and slowing down across billions of years. To pin down its value today, scientists deliberately use nearby galaxies because their light left recently and reflects the recent universe. Reach too far, and you start reading the expansion of the distant past, mixing eras together and muddying the number. So the nearby method draws its data from a modest bubble around us, a region small enough to reflect the present-day cosmos. The catch is brutal in its simplicity. That bubble sits entirely inside our hollow. The galaxies used for the measurement are all within the emptiness, all drifting outward, all contaminated by the same shared push. There is no way to average the drift out, because there are no undrifting galaxies inside the bubble to balance it. To escape the hollow, you would have to measure galaxies more than 1 billion light-years away, out past the walls in the normal universe beyond. But galaxies that far carry the expansion of a different, earlier era, so they cannot be used for a clean reading of today's rate. We are boxed in. The region close enough to give a present-day number is the same region tainted by the drift. Picture trying to measure the true water level of the ocean while standing in the middle of a giant, slowly draining tide pool cut off from the sea. Every measurement you take reflects the pool, not the ocean. To reach real ocean water, you would have to wade far past the rim, but by then the water is a different body entirely, fed by different tides. You are trapped reading the pool and calling it the sea. This trap is exactly why the illusion is so convincing and so hard to shake. The contamination is baked into the only data we can use for the measurement. Every careful team, using every careful method, draws from the same tainted bubble, so they all get the same inflated answer and all agree with one another. Their agreement looks like confirmation. It may just be a shared error, everyone reading the same tilted pool. And this is where the trap flips into a test, because the hollow's grip must weaken with distance. Its outward push is strongest near the center and fades as you approach the walls, vanishing once you pass beyond them into the normal universe. So the illusion should have a range. Measure the expansion using only very nearby galaxies, deep in the drift, and the number should run high. Measure it using galaxies farther out, closer to the walls, and the inflation should shrink, reach past the walls entirely, and the number should settle down to the true cosmic value. The deeper number read from ancient light. That fading is a prediction the void model cannot avoid. The illusion must decay with distance in a specific way, and that decay is something astronomers can hunt for in real data. If the expansion number gradually drops toward the deep value as you look farther out, the hollow leaves a fingerprint, and searching for that fingerprint became one of the sharpest tests of the entire idea. The hollow makes a promise it cannot take back. Its illusion has to fade with distance, and that fading is the sharpest test of the whole idea, because it turns a clever story into a specific prediction the sky can confirm or destroy. The logic is clean. The outward push is strongest deep in the center, where we sit, and it weakens as galaxies approach the dense walls. Beyond the walls, in the ordinary universe, the push is gone entirely. So the expansion number you measure should depend on how far out you look. Measure using only the closest galaxies, buried in the drift, and you get the inflated high value. Reach farther, toward the rim, and the inflation should shrink. Reach past the hollow, and the number should drop all the way down to the true cosmic value. That gives astronomers a concrete thing to chase. Take the expansion measurement not once, but at a series of distances. Read it close, then a little farther, then farther still, and watch what the number does. If it stays flat and high at every distance, the hollow is in trouble, because a real region-wide expansion would look the same near and far. But if the number starts high nearby and gently slides downward as you look outward, converging on the deep value, that is the hollow's fingerprint, exactly as predicted. Researchers have built detailed models of how quickly this fade should happen, calculating the expected number at each distance for a hollow of the measured size and depth. The models predict a specific curve, high near home, easing down as you move out, flattening toward the deep cosmic value once you pass beyond the walls. It is a precise shape, and precise shapes are exactly what scientists love to test. Picture the heat coming off a campfire on a cold night. Stand right beside it and you feel intense warmth. Step back and the warmth fades. Walk far enough and you feel only the cold night air, the fire's influence gone. If someone claimed a fire was warming the whole valley evenly, you could disprove it by walking away and feeling the heat drop off. The hollow's expansion boost should behave like that campfire warmth, strong at the center, fading with distance, gone past the edge. When astronomers compared the predicted fade against real measurements taken at different distances, the early results were encouraging for the void idea. The inferred expansion rate did appear to ease downward as the measurements reached farther out, drifting toward the deeper value in a way that roughly matched what an emptying hollow should produce. The fingerprint seemed to be there. That was a real point in the void's favor. A model that only explained the nearby number would be suspicious. A model that also predicts a specific fading with distance, and then finds that fading in the data is doing the harder work of real science. It stuck its neck out and survived a swing. Still, survived one swing is far from proven. The measurements at various distances carry their own uncertainties, and different teams read the trend with different confidence. A hint of a fade is not the same as a locked-down curve. The test is promising, ongoing, and hotly argued, and the fade is only one of several fingerprints the hollow should leave. Another involves the grand streaming motions of galaxies across our region, motions that should be flowing faster than the standard universe allows. Whole herds of galaxies, it turns out, may be racing in ways that fit the hollow and puzzle everyone else. If a giant hollow is draining itself, it should leave another mark, something you can watch directly. Whole swarms of galaxies across our region should be streaming outward together, flowing faster than the standard universe permits. And astronomers have found exactly such streams. Scientists measure this with something called the bulk flow. Picture drawing a huge sphere around us, then asking how the galaxies inside it are moving on average. If their private drifts point in random directions, the average nearly cancels, and the bulk flow is small. But if a large fraction of them are sliding the same way, the average survives, and the bulk flow is large. It measures the shared, coordinated motion of everything in the sphere. In the standard picture of the universe, Bulk flows should be gentle and should shrink as you draw bigger spheres, because over larger regions the random drifts cancel more completely. A vast sphere should show almost no coordinated motion, just the calm of a smooth cosmos. That is the expectation baked into our leading model. The measurements broke the expectation. When astronomers mapped the motions of galaxies out to great distances using a huge modern catalogue of galaxy speeds and distances, they found the bulk flow running fast and staying fast, even across enormous spheres. Instead of fading with size the way the model demands, the coordinated streaming persisted far out, at speeds the standard universe struggles to explain. By some measurements, this excess flow reaches a level of disagreement with the standard model as severe as the Hubble tension itself, the kind of gap that counts as a genuine crisis rather than a fluke. Two separate anomalies, the stubborn expansion number and these overfast streams, both pointing to something unusual about our region. And here is the payoff. A draining hollow predicts fast bulk flows. If matter across our region is rolling outward toward the walls in a coordinated slide, then galaxies over huge distances share that motion, and the bulk flow stays large exactly where the standard model says it should shrink. The very anomaly that puzzles conventional cosmology falls out naturally from the void picture. Picture leaves on the surface of a wide, slow whirlpool. Scattered across a still pond, leaves drift every which way, and their average motion is nothing. Caught in the whirlpool, they all circle together, and the average motion is real and strong, tracing the current beneath. The overfast bulk flows look like leaves caught in a current, and the emptying hollow may be the current driving them. Researchers fed the measured bulk flows into their void models, and the models could reproduce the fast, persistent streaming reasonably well, tuning the size and depth of the hollow to match the observed motion. That was another point in the void's favor. It explained not just the expansion number, but the streaming too, tying two mysteries to one cause. The match, though, is imperfect, and honest scientists say so. Some detailed features of the observed flows resist the simplest void models. The direction and exact shape of the streaming do not always line up cleanly with what a tidy hollow predicts. The idea explains the broad pattern while stumbling on some of the fine print, and that stumble matters, so the hollow needed still more tests, ones reaching even deeper into the past. And for that, scientists turned to the oldest sound in existence, a ringing from the newborn universe, frozen into the arrangement of galaxies, waiting to be used as a ruler. To test the hollow against the deep universe, scientists reached for one of the most beautiful measuring tools in all of astronomy, a sound frozen in place since the dawn of time, stamped into the arrangement of galaxies across the sky. Go back to the newborn universe, that hot fog before the first light broke free. In that fog, pressure and gravity fought each other, and the struggle set off sound waves, real ripples of pressure spreading through the glowing gas like ripples on a pond. These were the deepest sound waves imaginable, rolling through the entire cosmos at once. Then, when the fog cleared and light escaped, the universe cooled and the sound waves froze. Each ripple left a faint ring of slightly denser gas, a shell at a fixed distance from where it began. Over billions of years, galaxies formed a little more readily in those slightly denser rings. The frozen sound left a preferred spacing in how galaxies are distributed, a subtle tendency for pairs of galaxies to sit a certain distance apart. That preferred distance is astonishingly useful because we know exactly how big it should be. The physics of the early universe fixes the size of those frozen rings, giving us a length we can calculate with confidence. It is a ruler of known size, printed across the whole sky by the newborn cosmos. Astronomers call it the sound horizon, and they use it as a standard ruler to measure the universe. The method is elegant. Look at galaxies at some distance. Measure the apparent size of the frozen sound ring among them, and compare it to the true size we know it should be. How big it looks versus how big it truly is tells you how far away it sits and how much the universe has expanded to get there. A ruler of known length, seen at many distances, maps out the expansion history directly. Picture holding up a coin of known width at arm's length, then seeing an identical coin far down a long hallway. By how small the distant coin looks, you can judge exactly how far away it is. The frozen sound ring is that coin of known width, scattered through space at every distance, letting astronomers gauge the shape of the cosmos. Now bring in the hollow. The Void model makes a firm claim. Its influence must fade in the deep universe, so measurements that reach far out, past the walls, should match the standard cosmology and the deeper expansion value. The frozen sound ruler reaches across vast distances, deep into the normal universe beyond our region, so it offers a clean check on whether the far cosmos really does settle to the lower number. When scientists tested the Void models against the frozen sound measurements gathered over the past 20 years, the results cut both ways. The distant universe, measured by the sound ruler, does appear consistent with the deeper expansion value, which fits the Void's promise that its illusion fades with distance. The far cosmos looks calm and standard, just as the hollow requires. But the sound ruler also constrains how the hollow behaves closer in, and there the fit grew tighter and more demanding. Some versions of the Void model strained against the sound data, surviving only if the hollow took a particular shape and size. The ruler did not destroy the idea, yet it fenced it in, narrowing which versions could still be true. To pin things down further, researchers reached for yet another clock, one that sidesteps many assumptions by using dying galaxies as timepieces. Scientists wanted one more independent check, a clock that leaned on as few assumptions as possible. They found it in an unlikely place: dead and dying galaxies, used as timepieces scattered across the universe. The idea rests on a certain kind of galaxy, one that stopped forming new stars long ago. Its stars are all old, aging together like a single graduating class, growing grey in unison. Because we understand how stars age, we can read the age of such a galaxy from the color and character of its light. An older population glows one way, a younger population another. The light itself becomes a clock, ticking off how much time has passed. Now do this for galaxies at different distances. Nearby galaxies show us the recent universe. Distant galaxies, whose light left long ago, show us the universe as it was in the past. By measuring the ages of these stellar clocks at a range of distances and comparing how much they differ, astronomers can work out how much time elapsed between one cosmic era and another. That gives them the expansion history directly, era by era. The great virtue of this method is its independence. It does not rely on the distance ladder of pulsing stars and exploding suns. It does not lean on the frozen sound ruler. It reads time straight from the aging of stars, sidestepping many of the assumptions that other methods carry. When a fresh, independent method agrees with older ones, confidence grows. When it disagrees, you have learned something important. Either way, it is a powerful referee. Astronomers call these aging galaxies cosmic chronometers, and their strength is that they are barely sensitive to the very effects that tangle up other measurements. They read the passage of time in a way that is hard to fool. For a debate as knotted as the Hubble tension, an unfooled clock is worth its weight in gold. Picture a forest where you can tell a tree's age by its rings. Walk from a stand of young saplings to a grove of ancient giants, counting rings as you go, and you can reconstruct how the forest grew over centuries, without any calendar, reading time straight from the wood. Cosmic chronometers are like reading tree rings across the universe, letting the stars themselves tell you how much time has passed. So what do these clocks say about the hollow? The Void model insists that the deep universe, far from our region, should follow the standard cosmology and the lower expansion value. The chronometers reach far out into that deep universe, and by many analyses they do favor the lower value at great distances, in line with the ancient light. The far cosmos, measured by aging stars, looks standard and calm, exactly as the Void picture requires. That agreement is genuine support. Independent clocks, reading time in their own way, back up the claim that the distant universe expands at the deeper rate. and that whatever inflates our nearby number is a local effect that fades far away. Several separate methods now point the same direction for the deep cosmos, yet none of this proves the hollow causes the nearby inflation. It shows the far universe is standard, which the void needs. But standard behavior far away is also exactly what the ordinary model predicts on its own. The deep tests rule things out without crowning a winner. And now we reach the twist that makes this whole story dangerous for our best theory of the universe. The hollow does more than possibly solve one crisis. Its mere existence may break the very model it was meant to rescue. Here is the twist that turns a tidy solution into a deeper crisis. The hollow may solve one problem while creating a worse one. Because according to our leading theory of the universe, a hollow this big and this empty should barely be able to exist at all. Our best model of the cosmos is a careful recipe. It says the universe is built from ordinary matter, a large amount of invisible dark matter, and a mysterious dark energy driving expansion. Starting from the tiny ripples seen in the ancient light, the model predicts how gravity should sculpt those ripples into the cosmic web over billions of years. It has passed test after test on the grand scale, matching the overall pattern of galaxies remarkably well. It is the reigning champion for good reason. But the model also predicts how common structures of each size should be. Small clumps are everywhere. Large structures are rarer. Truly enormous features, whether giant clusters or giant voids, should be vanishingly rare, appearing only in the most extreme corners of the cosmic lottery. The bigger and emptier a void, the more the model insists it should almost never happen. Our hollow sits far out on that scale of rareness. It is huge, it is deep, and it surrounds us. When scientists calculate how likely the standard model is to produce a void this extreme, the odds come back tiny. In the champion theory, a region this large and this underdense is a freak, the kind of thing you might expect to find nowhere in the observable universe, let alone wrapped around our own galaxy. Picture a factory that stamps out marbles, almost all of them within a whisker of the same size. The recipe allows a rare oversized marble now and then, but a marble 10 times too big should essentially never come off the line. Now imagine reaching into the bin and pulling out exactly such a giant on your first try. You would not celebrate your luck. You would suspect the recipe is wrong, or the factory is doing something you do not understand. That is the bind. To use the hollow to fix the expansion crisis, you first have to accept that the hollow exists. And accepting that it exists means accepting a structure your best theory says should almost never form. You trade one deep problem for another, arguably larger one. The cure and the disease both point at cracks in the same model. Some scientists take the calm road here. Someone has to be the rare exception, they argue, and improbable things do happen. Maybe we simply drew the freak marble, and there is no deeper lesson. The universe is vast, and rare events occur somewhere. Perhaps somewhere is here. Others find that answer too convenient. When you are forced to invoke a one in a huge number coincidence to save a theory, they say the theory itself is whispering that it is incomplete. A model that can only survive by calling our existence a fluke may be missing an ingredient. The hollow, in this view, is less a coincidence and more a clue. That disagreement is not a small footnote. It sits at the fault line of modern cosmology, dividing those who defend the champion theory from those hunting for its replacement. And when researchers put hard numbers on just how unlikely our hollow is under the standard model, those numbers turned out to be brutal. The statistical wall the hollow builds against our best theory is staggering, and it forces a genuine reckoning. When researchers put hard numbers on how unlikely our hollow is under the standard model, the result was brutal. The emptiness we live in strains the champion theory to a degree that, in normal science, would count as a decisive break. Recall the scale scientists use to judge whether a result is real or a fluke, the same bar that confirms major discoveries. Cross it, and you have something genuine rather than an accident. The Hubble tension already sits well past that bar, and when researchers asked how badly our hollow clashes with the standard model, they found it crosses the same threshold on its own as a separate problem. The calculation compares our measured hollow against the range of voids the standard model expects to produce, its size, its depth, its position around us, all fed into the model's predictions. The verdict was that a region this extreme lies far outside what the theory comfortably allows, at a level of disagreement so severe that pure chance is a poor explanation. The hollow alone, setting aside the expansion crisis entirely, puts the reigning theory under serious strain. Then comes the part that stings. The hollow and the expansion tension are linked. In a matter-conserving universe, a big underdense region should produce a faster local expansion, which is the whole basis of the void solution. So the two anomalies are two faces of one situation. When researchers combine them, treating the giant void and the inflated expansion number together as a single joint problem for the standard model, the total disagreement climbed even higher, to a level where the odds against the theory become overwhelming. By that combined reckoning, the standard model is contradicted at a confidence that, taken at face value, would normally be called a refutation. In most branches of physics, a clash this severe would send everyone back to redraw the theory. That is how far out on the edge our hollow and its expansion boost sit when judged against the reigning picture of the cosmos. Picture a courtroom weighing evidence. One suspicious fact might be coincidence. Two independent suspicious facts, each strong on its own and tightly linked to each other, build a case that is very hard to dismiss. The giant void is one damning fact. The inflated expansion is another. Together, aimed at the same defendant, they make a case against the standard model that a jury would find difficult to wave away. Now, a fair warning, these sky-high confidence numbers depend on the assumptions built into the calculation, and different researchers make different assumptions. How empty the hollow truly is, how sharply its edges are drawn, how you model the odds, all shift the final figure. Critics argue that the most extreme statements overstate the case, and that with more cautious choices, the clash looks less fatal. The exact severity is genuinely disputed. Even the cautious critics, though, grant that the hollow is uncomfortable for the standard model. The debate is over how uncomfortable, ranging from a nagging tension to an outright contradiction. Nobody serious calls it a perfect fit. The champion theory is, at minimum, sweating, and that discomfort has opened a door. If the standard recipe struggles to grow a hollow this large, perhaps the recipe is missing something, or perhaps the deepest ingredient of all, gravity itself, does not behave the way we assume on the grandest scales. That thought leads to one of the most radical rescues on the table, a proposal to rewrite the law of gravity so that giant voids can grow after all. If our best theory struggles to grow a hollow this large, some scientists reach for a radical fix: change gravity itself. Rewrite the rule that has anchored physics since Isaac Newton, so that giant voids can form after all. To see why anyone would go this far, remember the problem. The standard model grows structure slowly, so enormous voids and giant clusters should be rare in the time the universe has had. If gravity were somewhat stronger on the largest scales, structure would grow faster. Dense regions would pull matter in more aggressively, and empty regions would drain out more completely. A stronger long-range pull could carve a hollow like ours in the available time, turning a near impossible freak into something expected. The proposal that does this is a modified law of gravity, one that behaves exactly like Newton's familiar rule in everyday settings, inside the solar system and within ordinary galaxies, but strengthens in the realm of very weak pull, out in the vast spaces between galaxies. Down here, apples fall as they always have. Out there, on the emptiest scales, gravity gets an extra kick. This modified gravity was first invented for a completely different reason decades ago: to explain how galaxies spin. Galaxies rotate so fast that, under ordinary gravity, they should fling themselves apart unless huge amounts of unseen dark matter hold them together. The modified law offered another route: strengthen gravity in the weak regime, and galaxies hold together on their own, no dark matter required. For years it lived as a fringe alternative, good at galaxies, doubted elsewhere. The Hollow gave it a dramatic new stage. Under this stronger, long-range gravity, the growth of cosmic structure speeds up. Voids empty faster and grow larger. Clusters assemble sooner and heavier. Run the numbers, and a region as vast and empty as ours becomes far more natural, the kind of structure such a universe would readily build. The freak marble becomes an ordinary product of a different factory. Even better, the same, stronger gravity drives faster outward flows from the emptying hollow, which feeds straight into the expansion illusion. The overfast streaming of galaxies, the inflated nearby number, the sheer size of the void, all of it fits more comfortably in a universe where gravity gets that extra kick on the largest scales. One change to the rules, several mysteries eased at once. Picture two bakers with the same dough. One uses a weak leavening and gets modest, evenly spread bubbles. The other uses a stronger leavening and gets dramatic, gaping holes and thick, dense walls. Our universe looks like the second loaf, full of extreme contrast, and the modified gravity is the stronger leavening that could explain the wild texture we see. This is a bold and controversial road, and most cosmologists remain cautious about it. The Standard Model, with its dark matter and dark energy, succeeds spectacularly on many fronts, especially in the ancient light, where the modified theories have a harder time throwing out a champion that works so well elsewhere to solve problems in our local neighborhood strikes many researchers as too steep a price. The alternative gravity remains a minority view, powerful in some arenas, unproven in others. So the Hollow forces a genuine choice. Accept a wildly improbable freak in the standard universe, or accept a rewrite of gravity that unsettles a theory that works. Neither is comfortable, and the field is split. Before crowning any winner, though, honest science demands we hear the case against the void itself, because not all the evidence has been kind to it. Honest science demands we hear the case against the void, and that case is real. Not all the evidence has been kind to the idea, and some of the sharpest challenges come from the very exploding stars used to map the cosmos. The first challenge is old and stubborn. Those reliable stellar explosions, the ones that serve as beacons across space, let astronomers measure how distance and light stretching relate to each other across the sky. If we sat inside a large hollow, that relationship should show a subtle distortion, a telltale bend caused by the outward drift near us. Early on, several researchers examined the pattern of these explosions and reported that it looked too smooth, too normal, showing less of the expected distortion than a big hollow should produce. To them, the exploding stars argued against a void deep enough to matter. That was a serious blow, because it used the same trusted beacons that anchor the whole distance ladder. If those beacons see a smooth, ordinary universe around us, then perhaps the hollow is shallower or smaller than the galaxy count suggested, too weak to fix the expansion crisis. A second challenge came more recently and cut in a different way. Researchers took the void model and tested it not against averages, but against the individual motions of a huge catalogue of nearby galaxies, checking galaxy by galaxy whether the pattern of movement matched what an emptying hollow predicts. Their finding was sobering for the void. To fit the detailed motions, the hollow needed to be far smaller than the size drawn from the galaxy counts, roughly a tenth of it. And a hollow that small does not fully erase the expansion tension. It helps, but it leaves a gap. Worse, in their analysis, the streaming flows predicted by the void models disagreed with the flows actually measured in the galaxy catalogue. The directions and magnitudes did not line up cleanly. The very bulk flows that seemed to support the hollow, when examined in fine detail, resisted the simplest void explanation. The idea that looked strong in broad strokes wobbled under close inspection. Picture a suspect who fits the general description of a crime perfectly. Right height, right build, right part of town. Then you check the fine details, the exact timeline, the specific movements, and the story stops matching. The suspect looks guilty from a distance, and less so up close. Some of the detailed tests put the Void in that awkward position, convincing at a glance, shakier under scrutiny. Defenders of the Void have answers. The measurements of galaxy distances and motions carry large uncertainties, they note, and different catalogues disagree with each other, so a mismatch may reflect messy data rather than a wrong idea. They also argue that the exploding stars, while reliable, are not perfectly identical beacons, leaving room for a hollow to hide within the scatter. The debate is very much alive, with reasonable scientists on both sides reading the same sky differently. What emerges is a picture in shades of grey. The Void idea is not dead, and it is not confirmed. It explains some things beautifully, strains against others, and depends heavily on measurements that are still improving. That is the honest state of the science, an unsettled contest rather than a solved case. And because the Void has not sealed the deal, other explanations for the expansion crisis remain very much in the running. Some of them abandon the hollow entirely and reach instead for brand new physics in the early universe. Because the Void has not sealed the case, other explanations for the expansion crisis are alive and fighting. Some of them ignore our hollow completely and reach instead for exotic new physics, planted in the earliest moments of the universe. The most talked about rival goes by the name early dark energy. The idea starts from a different suspect. Rather than blaming our local address, it blames the newborn cosmos. Suppose that in the first fleeting moments after the Big Bang, a strange, temporary form of energy briefly switched on, pushed the young universe around, and then faded away almost as quickly as it appeared. Why would that help? Because the lower expansion number, the one read from ancient light, depends on a careful chain of assumptions about the early universe. Slip a burst of extra energy into that early era, and it changes how the ancient light is interpreted, nudging the calculated expansion rate upward toward the higher nearby value. In this picture, the two numbers disagree because our reading of the early universe is missing an ingredient, and adding that ingredient brings them into line. This rival is attractive for a reason opposite to the Void's. The Void keeps the physics and changes our location. Early dark energy keeps our location ordinary, accepting that we live in an average place, and instead changes the physics of the infant cosmos. Two very different philosophies, aimed at the same crisis. One says the problem is where we stand. The other says the problem is what happened at the beginning. Both carry a cost. The Void asks us to accept a wildly improbable region around us, or a rewrite of gravity. Early dark energy asks us to add a brand new, never observed form of energy to the universe, switched on at just the right instant, and tuned to just the right strength to fix the numbers. Introducing a mysterious new ingredient, finely adjusted, makes many scientists uneasy, since it can feel like inventing exactly what you need to get the answer you want. There are still other contenders in the ring. Some propose that dark energy, the force driving expansion today, changes over time in ways the standard model does not allow. Others suggest tweaks to the number of lightweight particles in the early universe, or subtle new behavior in dark matter. Each idea rescues the numbers by adjusting a different dial, and each brings its own troubles and its own defenders. Picture a detective with several plausible suspects and no confession. One suspect had motive, one had opportunity, one fits the physical evidence, and none can be ruled out. Every explanation for the expansion crisis is a bit like that, compelling in some ways, flawed in others, none yet caught red-handed. The case remains open, argued in journals and at conferences around the world. What makes the Void special among these rivals is that it is the only one you can, in principle, go out and see. Early dark energy is invisible, buried in the first instant of time, testable only through its indirect fingerprints. Our hollow is right here, mapped in galaxy counts, traced in streaming motions, measurable with telescopes we already own. Whatever its final verdict, it is the suspect we can actually investigate directly. That may be the most important thing about it. The Hollow is a claim about our own place in the cosmos, one that better data will confirm or bury within our lifetimes. Which brings us, at last, back to you, standing under that crowded sky, and to what all of this means for our place in reality. So bring it all the way back to you, standing under that crowded night sky, and ask the question this whole journey has been building toward. What does it mean that we might live inside a giant hole in the universe? Start with the humbling part. For centuries, science has delivered the same lesson again and again. Earth is not the center of things. The sun is one ordinary star. Our galaxy is one among trillions. Each discovery moved us further from any special place toward the comforting idea that we live in an average spot, seeing an average view. The Hollow threatens to reverse that lesson. If it is real, we live somewhere genuinely unusual, in one of the emptiest large regions the cosmos has to offer. That would make us cosmic outliers, and outliers are dangerous for science, because so much of what we know assumes we see a fair sample of the universe. If our view is bent by the emptiness around us, then some of our most basic measurements, including how fast everything is flying apart, could carry a hidden slant we only now are learning to correct. The map of reality we have drawn might be sketched from an odd corner of the room, and the stakes reach further than one disputed number. The expansion rate ties into the age of the universe, its size, and the balance of what fills it. If our nearby reading is inflated by our address, then quantities we thought were settled shift with it. A whole layer of the cosmic story would need careful redrawing, all because of where our galaxy happens to float. Yet there is wonder braided through the humility. Sit with the strangeness of it. The emptiness around us is so vast that light needs 2 billion years to cross it, so deep that a fifth or more of the expected galaxies are simply gone. We may be adrift near the heart of the largest known void in existence, carried outward by a slow current that has flowed since near the beginning of time. Our cosmic address is stranger and grander than the average spot we once imagined. Here is the honest final truth. Nobody knows yet whether the Hollow is the answer. It might be the elegant key that dissolves one of the deepest crises in physics, sparing the laws of nature and blaming only our location. It might be a real but modest feature that helps a little and explains less than its champions hope. Or the crisis might belong to new physics in the early universe, leaving the Hollow as a spectacular curiosity beside the main event. The evidence points several directions at once, and the contest is far from settled. What is not in doubt is that we are living through the moment the questions are being asked. Better telescopes, larger galaxy surveys, sharper measurements of streaming and distance are arriving now, and within years, rather than centuries, they should tell us how big and how empty our region truly is, and whether it bends our view of everything. Picture a sailor who has mapped a coastline for a lifetime, then learns the tide gauge was mounted on a slowly sinking dock. Every measurement must be rechecked, every chart redrawn, and for the first time the true shape of the sea comes into focus. We may be that sailor, discovering the ground beneath our instruments was never quite still. So the next time you look up and the sky feels full, remember what surrounds it. A vast, quiet, wrapped around our galaxy, patiently waiting for us to understand what it has been trying to tell us all along.